Okay, that's not sure. Right. Yeah. So they might. So the way I'm looking at it, I think let's scroll down to the results. I think. I mean, if I'm looking at this, I can imagine multiple scenarios where we would say that you usually have more scenarios. So, do you still have it set up, or do you have access to set up? Do you have somebody who can access set up? This is all in right? Whose lab is it? Your personal manager? To decide whether so I'd be more than happy to take a look at it. Is that what you asked? Very happy to. Usually the pushback comes in when they say that certain scenarios have been done and they say that it's too shallow. Oftentimes that's what people look at. So wait a couple of minutes or start? Oh wait. You can start. All right. Hi, everybody. Good morning. Welcome back to our session on traction motors. So we've been talking so far about a lot of kinds of motors, and I know the title right now says fundamentals of SRMs, but it's just that when I combine all of them, the title that stayed on the top is fundamentals of SRM, but it's actually day 5. It includes all the content, the topics that we had talked about in the outline. Is all included in one single slide deck. So I didn't want to create a bunch of presentations that connected separately. So on that note, right now, before we go forward, I wanted to mention this. In a lot of the papers that I have mentioned, cited here, I have given you some references. Please feel free to look them up. Some of them are my publications, but several of them, I've tried to be not biased towards the work that only I have done. So try to be, sort of provide some perspectives and some references from other authors who have done some really good work in this area, or all the topics we have talked about so far. You're always encouraged to reach out to those professors, to those students who have graduated, and ask questions if you need. That's always the best way to go forward. So let's start with the basics of switch reluctance motors. So when we talk about switch reluctance motors, the first thing is that people think about switch reluctance motors as being relatively new, that permanent magnet has problems and then it came around to being a motor that is accessible. Quite the opposite. It has been around since the mid-19th century. So it's been around for a very long time. And the reason it became very popular is because the technology, the electronics that was used to drive the motor was not as mature as it needed to be, specifically to give you high precision control. The benefits we have already know. It doesn't have any coils. I'll show you a little bit about them as we go forward as well. It's very robust because we talked about yesterday, when it gets hot, permanent magnets can demagnetize. Copper wires can have insulation failures. You can have windings that get too hot. If you don't have anything on the rotor, that allows your motor to be a lot more robust. It's more survivable, and things don't go wrong. As a result, it's also able to go to ultra high speed operation. It can operate in both torque and speed regions, basically, which means you can be in all four quadrants. We showed yesterday what the adjustable speed drive quadrant looks like for torque and speed. And of course, this basically has a unique feature or unique attribute that your inductance is a function of its rotor position. So that's definitely something that none of the other motors have in quite as much detail. So just to give you a quick snapshot view of where things are. I mean, if you look at the material cost for a traction motor, your permanent magnet is one of the most expensive components. This is based on data from some time back, but the numbers have only gotten worse since. If you look at the reserves in terms of metric tons, China has the highest reserve of rare earth material. And in terms of the number of the market report that you see, there was a huge spike that happened in the permanent magnet cost, which basically is the dollars per metric ton. That huge spike that happened right around 2011. It's come down, but at the same time, like I said before, it's closer to 50, where it used to be about, I guess, more than 10 years, 12 years back, it used to be less than $30 per metric ton. That's $30,000 per metric ton. So if you look at it, like I said, this is the innards of a switch reluctance motor. The coils are concentrated, which basically means you don't have to wind them across. Instead, you can form them ahead of time, and you can put the mica tape on it, and then you can insert them. This specific one is a switch reluctance motor. It's actually one of the ones we have in the lab that we use for teaching as well. The idea of this SRM, essentially, you will notice that it does not look like it has teeth. It does. It actually has a filler material that covers. That's why you see the difference in colors. It just makes sure that you don't have as much of a windage. So the rotor does not necessarily have to have aerodynamic resistance, so to speak, in the motor. But typically in most motors, you will see, and I'll show you some as well, you will see that they have teeth on the rotor and the stator. So that's what's called double saliency. Double saliency basically means you have teeth, salient teeth, both on the stator and on the rotor. This motor is known to have a very small air gap. That is both a benefit and a shortcoming. When you have traction motor drive type applications, the challenge tends to be that there are concerns about how much clearance you need to have for the motor to operate. But on the flip side, it gives you the ability to transfer power from the stator to the rotor very effectively. Like I said, it can, as a result, it can cool easily. This is a typical configuration for an 8-6 machine. The way the configuration is broken down, it's the number of stator poles slash the number of rotor poles. So if you have 8 stator teeth and 6 rotor teeth, it would be called an 8-6 machine. 6 and 4 would be called a 6-4 machine. 12-8 is called a 12, so on and so forth. It has high reliability, but one thing that you can notice is that if one of your coils goes out, in that case, the other coils can continue to operate. The way the control is set up, is that the phases are not they're not dependent on each other. Also, this torque speed range has a much longer constant power region. So you can go to much higher speeds of operation for this motor, which makes it a big benefit. It has negligible mutual coupling. It has the ability to start with any number of phases. So you don't have, unlike an AC machine in which typically you have 1, 3, 5, 7 phases, switch reluctance machines can also have even number of phases, and nothing necessarily gets in the way. You just have to design the rest of the system to match. So the challenges that we see, which is primarily the reason why the motor is not the only one, the primary contender, is first and foremost, you have high magnetic and control nonlinearities. The motor itself operates in high saturation region. If you remember what high saturation is, it basically is a region in which you apply current, you increase the current, and the flux does not go in proportion. So if you double your magnetic field, if you double your H, or magnetic field intensity, your flux does not double. That means now you have a non-linear behavior in the motor. You have different variables that affect aspects of vibration, acoustic noise. Because it has a small air gap, it has radial forces that actually create deformation and cause acoustic noise and vibration to happen. There is an interdependence between the converter and the controller that actually has to be carefully managed. Your sensitivity to design and manufacturing tolerance, we had some conversations yesterday about how the motor can be designed, but when you're designing it, and if you don't have the right amount of clearance, you can have an asymmetry in the motor itself, or you can get to a place where your tolerance is much more than what your air gap requires it to be. So in terms of the control scheme, if you look at the control scheme, the scheme itself is not very complex. So I think my language there is somewhat misleading even as I read it. It's not as much the control scheme being complex, it's more that the converter topology tends to be a little more involved, and the control itself, you are just doing simple current control. You're doing hysteresis control, which is one way to do it. There are some people who have proposed ideas like sinusoidal control of current, but predominantly what you would see for switch reluctance machines is essentially the hysteresis control. So you can generate a high amount of torque ripple just because you have turning on and off of the phases. That can also be managed by controlling the current. We will talk about some of this later. It can generate high levels of acoustic noise. It's a design feature. It's something that can be modified. It can be managed by designing the motor properly. You have to have, there are lots of research articles that have been written specifically on shaping of the rotor, placement of the windings, distribution of the magnetic field, creating flux barriers, and so on and so forth. So lots of ideas do exist like that. It also has a fairly high levels of friction and windage losses, which is because it has a salient rotor, which is why you saw in that previous example, it was covered on the rotor so that when you spin, it would not give you, because that also adds to the noise as well. So that does not give you any of the noise from the mechanical side. So application wise, there are several applications. Transportation, keep in mind, when we talk about transportation, we cannot just talk about vehicles on the road or land vehicles, right? You also have air, and you have marine as well, so naval applications. And then of course, take it one step further, you also have aspects of space applications, and that's also an important component. So in terms of the high-speed generator application, it tends to find a lot of use because it has the ability. So if you have a gearbox that can step the speed up, the generator can be much smaller and can give you a much more compact design. Domestic appliances actually have seen some use for it. There have been some manufacturers who have made washer dryers, not dryers, washing machines, garage door openers, pumps and such. Any place like spindle or something that requires high-speed operation, SRMs can be a very good solution for that. So as we start talking about switch reluctance machines, a couple of basic definitions that you need to know and recognize. The first one is called aligned position. The name kind of gives it away, right? Aligned position is the condition in which the teeth on the rotor and the teeth associated with one phase on the rotor, on the stator, and any one set of rotor teeth are aligned. So they are basically facing each other. I'll show you what that looks like in a figure in just a second. Unaligned position is the furthest your rotor tooth can be from the stator. And sensorless control is the method of implementing the system without a position sensor. Like I said, you need to know how to turn on and off the switch reluctance motor, which means you need to have accurate information about where this current excitation needs to be applied. If you are able to create a system where you can use the terminal measurements to identify this and to identify the position, that is very beneficial, because then that allows you to create a sensorless control, which can be cost effective as well. So, but before we go there and we're talking about the idea of aligned and unaligned position, if you have multiple phases, just to give you to kind of ask that question, what do you think if you have, does any motor that you have come across, does it sound in function like a motor that you might recognize? Is any motor that you think about? in terms of similarities, it does have some similarity to what you would do with the stepper motor, right? In which you're basically creating motion. Now, as you're doing something like that and you have unaligned position, you basically creating the concept of an electromagnet, which is attracting a piece of metal. What that means is that whenever your motor, the rotor is trying to get aligned, if you are not careful, you can end up into a situation where your rotor goes and it comes to a sudden stop. It would be very similar to when you are driving. If you don't recognize the stop sign, or if you don't know where your stop sign is and you don't apply your brakes until you have to stop, you will get that massive forward motion. The same thing happens for the motor as well. So there is a need for awareness to recognize when the phase needs to be de-energized and what that dynamic setup is going to be. So we'll talk about a lot of that as we go forward. So in terms of the operation itself, like I said, it has saliency. The rotor also has saliency. You have windings that are concentrated, and it has a shaft in the middle. This is for a conventional radial design. So if you look at most of them, you see that your configuration for a switch reluctance machine would be somewhere around NR is equal to number of rotor poles is equal to number of stator poles plus or minus 2. Actually, that's not exactly plus or minus 2, because as you increase the number of phases, that flexibility can go up a little bit. Like you can have something like a 12/8 machine, for example, which is not plus or minus 2 per se, but the number of poles do go on the lower side. So this is an example where we have compared what it looks like to have a 3-phase and a 4-phase switch reluctance machine. Both of them have concentrated coils. They both have individual phases that are excited. This is an 8x6 configuration, 8 teeth on the stator, 6 teeth on the rotor. And this is essentially the motor where if you energize, let's say you have a condition like this, the way you identify the phase you are going to energize is by identifying which one has the rotor that is closest to that position. If you're trying to, you would energize phase A because this pole here, if I give it a number as 1, pole 1 is the closest to phase A. Now here's the catch. If you by any chance instead of phase A energize phase B, what would happen is this rotor would spin backwards. What that means is that there is no existing orientation on the rotor that requires this motor to spin one way or the other. So you have to, as a control designer, as an electrical engineer, you have to decide how you are going to design this machine. If you end up in a scenario where you have 2 rotor poles that are almost equally close to any one given phase, what would happen? What do you think would happen? If you have multiple rotor teeth that are close to one phase that you're trying to energize, what could possibly happen? Exactly. Right. So depending on how much current you applied to that one phase, and depending on whether there is even a small difference, there will be a force. Basically, it's a tug of war, right? It's going to be, it'll try to attract, both of them will try to attract themselves to the stator. Whichever one is higher, obviously, probably will end up winning, but you'll create a lot of loss because it will try to go across both of them. So the one thing about an 8/6 switch reluctance machine that is unique, and I won't talk about that very much, but you can look up a paper that's written on the topic of auto calibration model for a switch reluctance machine. We wrote that several years back, but we have taken that forward for a 610 machine since then. The idea here is in an 8/6 machine, there are some very predefined steps. So first and foremost, you apply current here. The closest pole that you have aligns itself, and this goes from unaligned to aligned position. So when you're talking about unaligned position, the pole, basically, you will notice one pole is far from the stator, but there is another one that is halfway. It's not entirely aligned, because even if you look at this position here, when this is completely aligned, there is another pole here that is very close to alignment. So an 8/6 SRM has one unique attribute, that you're able to get a clear unaligned, aligned, and what's called a midway between aligned and unaligned. The reason why this is important is because when you start looking at modeling a switch reluctance motor, the ability to identify, just align one single phase and do all of your measurements to create a mathematical model can be very time efficient. And that is the work that we published quite some time back. So here, what you see is an alignment between phase A and one of the poles. One more thing to notice is just like an induction machine, there is no well, induction machine has an orientation once it has mutual coupling, but here the rotor tooth is not biased in any way. The rotor is not biased in any way. After this, if you energize, let's say this is phase A, B, C, D. Let's say you energize phase D, it will spin backwards. It'll go the other way. That's obviously not going to be good for you, especially if you're talking about traction application. So this is essentially is the 6-4 SRM, just to show you how this works. I normally would use an animation, but since an animation doesn't work, I'm using figures here. So you go from the aligned position for phase A prime, and then you align. So phase A is aligned, and then you can basically align either B or C. Depending on which direction you want to move, you would either align phase C prime or B and B prime. So in this case, if you align C and C prime, that means your motor is going from position here, you are now going clockwise, right? So you go clockwise, and then you have now energized this one. Move it again, you start energizing B. So your sequence essentially is going in a clockwise direction. You're energizing your motor. So if you go like this from the beginning, it starts to show up. So that's basically how the motor operates. All you're doing is you're identifying the sequence of excitation, and you are identifying the instant of time at which the current needs to be applied. Like I said, since the position is moving and it's a dynamic variable, when this position changes, the first thing you always have to remember is that if you energize the phase at the wrong time, you can get negative torque, right? So you can basically, I mean, it won't cause your motor to spin backwards, but you will definitely incur more losses. So the field distribution of an 8-6 SRM, and I'll show you some alternate field distributions later, one of them at least, later. This is essentially called long flux path. Long flux path just means that the flux in the stator goes to the rotor through the back iron, and it closes its shape in the form of a D. Now, for other kinds of machines, it would look different. If you're talking about a 12-weight machine, or if you're talking about a 610 or 12-weight machine which have more than 2 poles being excited, that field distribution could look different. And this field flux density here is very low. I was just using this simulation just to show you what this field looks like. In terms of the inductance behavior, like I said, when you are at an unaligned position with respect to phase A, you have no flux, which means there is a certain amount of inductance that exists. Can anybody tell me what that means when we talk about unaligned inductance? What is unaligned inductance? Like, how is it different from aligned inductance? Should that unaligned inductance be 0? If not, why not? Sure. So, but should it be 0 then? Sorry. It is rotative flux, you're right. Exactly. This is like, it's not like an electric circuit. When an electric circuit, if the circuit is open, nothing's going to flow. But in this specific scenario, your rotor is still within the range. If it was completely far off, if the distance was high enough, then this number would have been much lower. This, by the way, it's not a number, it's just an illustration. So the goal for us, even as we design an SRM, and we will talk about it later, is to lower this number as much as possible and increase this number as much as possible. The ratio between the aligned to unaligned inductance is referred to as saliency ratio. The saliency ratio is the ratio between the aligned to the unaligned inductance. We want this number to be as high as possible. So if you move from here and your rotor now gets closer, you start to see an increasing profile for your motor, for your inductance. Once it gets to aligned position, that's where your inductance has peaked. That is the point of the least amount of air gap, which means you have the least reluctance. So majority of the flux is has linked now with the rotor. This is the closest you can get to the value. Now, the smaller the air gap, the higher this number is going to be. The smaller the air gap, the more questions about reliability you're going to get. So that's where that trade-off has to be considered. The same thing now, as we move away from the aligned position, inductance starts to trail and fall. and then at the very end, you go back to unaligned position. So this is considered to be one electrical cycle, right? So this is one cycle in which your machine goes from unaligned position back to unaligned position. That's considered to be one electrical cycle. So if you look at all 4 phases for the motor, this is actually one of the motors that we had designed quite some time back. This was I want to say 2 kilowatt motor, if I'm not wrong. It was a 2 kilowatt drive and a motor with a drive that we created. And this essentially has an inductance that maximum was 730 or something microhenry. So one thing to keep in mind is, right? Yeah, but yeah. So one thing to keep in mind for something like this is that if you are looking at an inductance that goes to the of millihenry to henries, that's difficult to do because you're talking about having a much more, right? The footprint is small. So unless you're talking about a machine that is massively big, it's like capacitance. The numbers will not be quite so dramatically high, which means your modeling has to take that into consideration. What you see here is that as the rotor moves from one point to the other, each one of the phases has an alignment that happens before the entire cycle is over. So let's say this phase here, phase C, is our initial, like that's the phase of reference because it's in the middle of the screen, it's just easy to point to. But there is a phase right before that, and there is a phase right after that that actually has an overlapping inductance, which is, if you apply current here, you can have a direct effect. If you apply current here, it'll have a complete different effect. Like I said, you have phases nearby that can be energized, which can lead to negative torque. How that happens, we will talk about that in just a little bit. So we spoke a little bit about the idea of coil winding and basically the circuit equations yesterday, right? The basic equation for any based on KVL for an electric motor is V is equal to Ri plus d lambda dt. You can break the d lambda dt once again into L times I because lambda is equal to Li, and then that gives you L di dt plus I dl dt. If you separate them out, excuse me, if you separate them out and you get L di dt plus omega I dl d theta, what this gives you is there are 2 key variables that begin to come up. If you go back to the equation for a DC machine, what was the equation for? Does anybody here remember the equation for back EMF of a DC machine? K times IF times omega, right? And your DC machine, the torque equation was K times IF times IA, right? So what we remember here is that my back EMF is a function only of the field component. My torque is a function of both field and armature. So the idea was change the armature, you can change the torque, change the field, you will affect both, right? So how you apply current is what we try to do also when we talk about vector control, field into control. We went from there. The same equation applies here as well. So you have I omega plus some term here, right? So it's similar. So if you consider this, just because there is no separation between IF and IA, we only have the phase current IP. All right. So this is a function that is this is the variable that is a function of your applied speed. And when you are a function of applied speed, that becomes your back EMF. So the first term here gives you the voltage drop across the winding. The second term gives you the inductive drop. The third term gives you the back EMF. If you want to convert this to a power equation, what would you do? I mean, it's circuits 101, right? We have voltage, we want power, multiply current, which means when you go into the circuit, what you get essentially is you have this term is the motor term. Now, just take a quick pause here for a second. This is voltage drop across the resistor. Is that power transfer or is that power loss? It's loss. It's a loss in the winding resistance, right? To be more specific, this technically it's stored. Stored in what way? Is it usable by the motor? Is the question. It's stored in the winding. It's stored in the winding. You are correct, but it's not. It's an inductive drop. It's stored in the core of the motor. What will that cause? It does cause a loss. It's not fair to say it's completely lossless necessarily, but what does inductor do? What's the function? The basic function of an inductor? It stores energy in what form? If it's magnetic form, then what is it going to do? Once the source is gone, what does the inductor do? It dissipates its stored energy, right? Whatever the magnetic field has been stored, that energy is dissipated. So that will then lead to current that does not go straight down. If you had a purely resistive circuit, your current would have been a straight drop, right? Because of the presence of the inductor, it will gradually discharge and creates a tail. It basically gives you a slope which has a time constant, RL circuit, right? That's what we have done in circuits. Every single circuit course, you talk about the RL circuit. The last term here is the term that is going to with your back EMF. This is the power that the motor actually is. If you break it down, the first part is the winding, and the second part is the core. The third part is the actual motor where your energy conversion happens. So if you want to convert this to power, multiply by I and then divide it by speed, and you get what? Power divided by speed is torque, and that's what gives you here. So you have these half I squared dl to d theta is the torque that you get from the electric motor. What this tells you is that because torque is a function of square of current, what does this mean? It gives you a unique attribute about this motor. The polarity of the current has no relevance. You can apply positive or negative current, you will still get the same torque. However, what does give you negative torque is if your dl to d theta is positive or if it's negative. What that means is, depending on where you apply the current, you are going to either get positive or you're going to get negative torque. Now take this back to this inductance profile. It matters because if you apply current to this red phase leading edge, you will get positive torque. If you by chance the same region apply current to the green, which is phase B, which is the trailing edge, you will get negative torque. So it matters a lot as to where and which phase you select. If you select the wrong phase, you will end up with torque that is going to be negative. So essentially the ideal waveforms are where you go for the trailing edge, the leading edge you apply if you want to run it as a motor. If you want to run it as a generator, you apply in the trailing edge. So as long as the speed is positive, you'll get negative power, which means power flows from the machine to the supply. This gives you a quick understanding of what the flux linkage versus current looks like at different rotor positions. This is for different values of current. What you see is that the flux linkage at unaligned position is nearly a straight line. Why is that? Because it's not saturated. You're on the linear region of your BH curve. As you start increasing your current and you get closer to aligned position, now your flux linkage is much higher. You're going to saturation region, and now your flux linkage is no longer linear. As you increase the current, the flux starts to plateau out. You end up getting a flat region, which means closer to aligned position, you need to be careful about how much current you're applying because that is going to give you some losses. So the idea of co-energy, essentially, if you haven't come across right now, I'm not going to go into the fundamentals of magnetics, but the idea of co-energy basically exists to calculate the amount of work that is done in a given system, right? So if you're talking about the area under the curve in the flux versus current profile, the rate of change, the change in co-energy over the change in angle is what gives you the amount of torque. That is the magnetic representation or the work representation between aligned and unaligned position. What that means is that if this area under the curve is bigger, then the torque that you're going to get is also going to be higher. Even if you go back to the equation here, this equation is given as I squared dl d theta. So if your dl d theta is higher, which means it has it's sharper, right? It has a much sharper slope. That means dl d theta for any window of time will be higher. So if you can increase that saliency ratio, correspondingly, your ability to generate torque will also be higher. So if you talk about this now, the average torque expression is given as M times NR, where S is basic stroke is equal to M times NR, and the average torque is given as S times del, basically it's co-energy, rate of change of co-energy with respect to the angle. Why is this important? It is important because this led to an invention that allowed us to basically currently is being used in several commercial applications. It showed us that the S, which is the number of strokes per electrical excitation, directly impacts the average torque you're going to get from the motor. If you can increase the number of strokes in the motor, you get a much better average torque. Think about it this way as well. If you have a, let's say, a simple idea of like a stepper motor, but let's simplify this even further. If you guys have ever played as a kid with a tire or something, we did, you probably did not. But when you roll it, or even if you're riding a bicycle, let's keep it simpler. If you're riding a bicycle, if you pedal and then you let go, the speed starts to drop, right? So you are going to get the smoothest performance with how many times you pedal per revolution. The more you pedal, the more your speed is going to be constant, right? Same thing applies for your car as well. If your foot is on the throttle, on the accelerator for a good amount of time, there are also people you might have seen, and they're not difficult to spot because they press on the accelerator pedal and then they let go. And you can see because the car kind of speeds up and slows down. That idea exists here as well, which means if you increase the number of times that you are going to press that pedal, or even for that person, the car is going to appear to be smoother than it would have been otherwise. So those are very examples, not always accurate because I'm giving you very anecdotal references. But the idea basically is you can use that information to design a new family of machines, which is what we did. So if you're talking about the model of power electronics and controls, the breakdown is fairly straightforward. You have the power electronics. We will talk about converters in some more details later. But the idea of an SRM is that each phase has two terminals. Unlike what you get for AC machines, where you do not have access to the neutral point, in the SR, you do. Well, you actually don't have a neutral, you have individual phases. Each phase, you can connect to them individually. What that means is that you can apply current, or you can apply the phase winding in between the two switches. This is a phase leg you would get for a typical converter. If I show you this converter here, what are some unique attributes you might recognize or identify? What can and cannot happen? You cannot have shoot-through fault. Does everybody here know what a shoot-through failure is? Is anybody here who does not? Okay, I'm glad you asked. So shoot-through failure basically is the possibility where you end up, because normally if you have a full bridge where you have multiple switches, you might turn on one phase and it runs through the phase winding to another. But there are two switches that are kept next to each other, and the phase winding is connected from the midpoint. If normally the way you operate the system is that you turn on the top switch and the bottom switch for another phase leg. The problem that happens is if you have an overlapping time between S1 and S2, because you are turning off S1 and you are turning on S2. And if they have a little bit of an overlap, this power supply gets short-circuited. So in the SRM, because of this configuration, this converter is inherently reliable and can eliminate shoot-through failure completely. This topology, if you break it down, it looks fancy. It's an asymmetric bridge, but if you break it down, it's the same idea as the full bridge, but instead of the switches, we have a switch here, flip the inductor, you will get a diode and inductor. So it looks very much like a conventional bridge rectifier with two switches and two diodes. It just looks fancy because we have connected the points at a funny angle, right? So this is an overall, this is a simplistic breakdown of what this topology looks like. And this is the feedback loop. If you're designing control for switch reluctance machine, this is the feedback loop you get. Based on that, the converter current essentially looks like a choppy trapezoidal waveform. Why? Because what we're doing is called hysteresis control. Everybody here knows what that is? Hysteresis control, basically also known as bang-bang control. As engineers, I always want to, I think we are very innovative, but when it comes to naming things, we are horrible. We give names to things that are very, very literal. At least that's what I can imagine, because this is bang-bang control. You have a band, it goes up top. I'm guessing it hits it, makes a sound, it comes down, hits it, makes a sound, hence the name. There might be a smarter reason for it, and I'm seriously hoping there is, because this one sounds too childish, even for me. So the idea here basically is you have a phase winding here. You're trying to apply a constant current to this phase winding. So you apply pulses of voltage to the phase, and you control the current. The width of this pulse of voltage is a function that is dictated either by PWM, in which you might have a fixed frequency, the duty cycle, or on a DSP, you can use a GPIO pin. You might have come across GPIO pin, a general purpose input output pin, in which you can apply a signal and then indefinitely wait and then apply the turn, take it off, or apply another signal, right? That's the job of a GPIO. The difference, of course, is that that means your system does not have a direct switching frequency, because you are essentially varying it as need be. The benefit that it could be is that you are able to control the current more effectively So even if you end up having to have a 0 duty cycle, which normally you don't do, a 100% duty cycle, which also you don't do, this allows you to let the current go as high as it needs for as long as it needs. So you do that and you apply current. Keep in mind, this tail that we got because of the inductive effect, you have to take into consideration. Based on the equation we saw for the torque, what would happen if I applied current and this current here extended past this line? What happens? Torque. That's right. That's exactly right. Yeah. Right. So no. So torque is given as I squared dl d theta, right? Which means if your dl d theta is flat now, in reality it won't exactly be flat. It'll be very close to being flat. It's got a little bit of a curve to it, but it'll be very close to being flat, which means your torque is going to be nearly 0, which means if you apply here, that power is going to go as losses. It's going to show up somewhere, right? So this trailing current has to be taken into consideration. This turn off period has to be taken into consideration. If you don't do that, and if you turn this off too late, you might end up getting into the next region, into the negative torque region, and end up creating negative basically motion or negative instead. You can break down the operational region of an SRM into multiple regions. You have the near zero, you have standstill, constant torque, constant power, and then this unique part that is called ultra high speed region. In the SR, when you're talking about current, this profile starts off being very easy to control because inductance is a function of position. By definition, at low speeds, this period is going to be very large, which means you have a lot of time available to control that phase. As the speed increases, this window starts to get narrower, which means now what is getting taxed is your DSP, because your ADC, the analog to digital conversion, and your switching signal has to happen very quickly. If you want to regulate this band and keep it as tight as possible, you have to sample the signal, process it, and apply a switching signal very, very quickly. If you don't do that, you'll end up with a much larger current ripple, which will lead to a very high torque ripple. So when you go to ultra high speed region, this actually can lead to a condition that's called single pulse mode, because in some cases, what happens is this is so narrow that you barely have enough time to apply one pulse. The current goes up to its rated value, and then it has to be turned off and the phase is off. That's called single pulse mode. Single pulse mode can give you a much higher torque. It can give you efficiency increase as well to quite an extent, but it can lead to a massive torque ripple because you're not controlling the current. So you can increase the efficiencies, which is quite interesting. You can get, because you're applying those pulses so quickly, you can increase the efficiency to mark it up. You can get some higher average torque in some cases, but the ripple will be quite noisy. So if you look at the comparison between all the motors that we have talked about until now, and once again, I will tell you, if depending on who you are talking to, they might have a different version of this table. And because every one of us knows the ins and outs of each technology they work with. I work with SRMs quite a bit, so I do see the benefits of an SRM. If you go to somebody who's very much into AC drives, inductions and such, their version of this might look very heavily in favor of induction machines. I'm not saying one is not right, the other one is. It's just that we know more about the pros and cons of each topology because of the number of years we spent on that. So just with that caveat, I wanted to mention SRMs have a substantial benefit when it comes to wide speed range. That's an established fact. It also is robust because there is no magnet, there is no copper. So I am fairly well convinced that this motor has a substantial feature. I'll put that out there, and at the end I'll ask you what you think about SRM. This is not me giving you the answer now and then asking you the same question later and hoping that I can convince you, but the point remains. Now, if you take it once, actually, let me finish this one here. PM machines do have the benefit of high efficiency. That's the standard we are trying to beat. There is a paper by Professor Akira Chiba from Tokyo Institute of Technology. That was one of the earliest papers that I saw where he did a direct comparison of traction motors, where he showed that the SRM is capable of getting efficiencies as much at the same level as Toyota's IPM. So he showed that a switch reluctance machine is capable. Since then, we have actually developed the machine we have worked on called high rotor pole switch reluctance machine. There's another motor family that there's a group in McMaster University in Canada has also been working on. NIDEC has some success there as well. So there are several groups that have shown that switch reluctance machine can do, but Professor Chiba's work was one of the early works that showed at full scale that they were able to accomplish that level of power. Induction machines, generally speaking, I don't want to say don't have any benefits. They do. They are robust, mostly because the technology is very mature. There is a wide speed range to quite an extent. You can have open loop control, apply line frequency, the motor runs. None of the other motors can do that. So in terms of design procedure, so just so you know, today's session is going to be a flow through like I did yesterday as well. And we will take breaks when we get to the point. We'll take a break and we'll kind of keep catching up as we go. But I didn't want to separate the topics out so much that I'm starting a brand new topic every 30 minutes. So the design procedure of the SRM is very much like what we have done for the other machines. You start with the initial geometry based on the constraints. You have material selection, electromagnetics, post-processing, static requirements, winding configuration, dynamic performance, which has a whole slew of things. The one that you might not see in most other motors, people won't talk about the vibration acoustic as much because they assume that PM machines are quiet anyway. But for SRMs, we do keep that into consideration. This, once again, goes back to that simultaneous coupled operation or co-design method that I was talking about. From that, if they don't meet the requirements, you close the loop and you take it back to the geometry. Keep in mind, in every scenario, whenever you make a change to a geometry, you have to consider whether or not your geometrical constraints have been met. Some of the mistakes that even we have made along the way was one of the times we did not take into consideration a standard housing. We assumed that because it was a brand new application, that we could select the stator size and we could machine out the housing. The challenge was the solution was expecting us to meet certain standards for NEMA housing. So NEMA standards for the housing, and they wanted to have an pre-existing frame that they could use for the motor. So we ended up having to redesign the stator to a good extent because we did not take into consideration specific requirements that came from the application. So in terms of the number of phases, how do you go about it? The first thing is you have to make sure that your motor can start from any position. Like I said before, if you have a condition where you apply current to one phase and there is just no way, it is locked in place, you cannot apply current anywhere to make it move, you have a problem. So you do need to consider how many phases you can have. The second one is the ability to operate bidirectional mode. You need to be able to spin the motor both clockwise and counterclockwise. Think about traction. You don't want to just move forward, right? You also want to back out sometimes. I mean, unless we have one of these designs in which your wheels spin, short of that, you're going to have your motor spin backwards, right? Or turn backwards. So reliability is another factor. You have to start looking at it. How long are they going to handle it? Do you have enough space, enough clearance for them to be air cooled or passively cooled? The cost, how much is that going to cost you? How many phases? More number of phases is more number of switches. That many coils that need to be formed, that increases it as well. Power density, you can give, if you have higher number of phases, that gives you a better or like a flatter torque. You have lower losses. You can end up with more power density. Of course, it comes back to if you make a wrong selection on the winding type, you go back to where you have more copper losses. The power density goes out the window again. So this is just now I'm going to go through some of the design variables, and that's where I won't spend a ton of time. We have some articles that we have on this topic that I've also added as reference. There's a specific article, I think I had mentioned that later, that you can refer to it on design considerations as well that you can take a look at. But in terms of the geometrical constraints, if you are coming up with an analytical or a FEA model, your typical variables for the machine are going to be the yoke, the pole length, air gap, and the rotor pole length, the rotor yoke, and the shaft radius. This is a cut and rolled design for the switch reluctance machine. In terms of the number of stator and rotor poles, the electrical frequency of excitation is directly related to how many poles you have on the stator and how many poles you have on the rotor. If that number is higher, in that case, your electrical frequency is going to be lower. So if that difference is high, your electrical frequency is going to be low. So you have to decide what you want. So high number of poles or poles per phase are a good choice if you want to go at lower speeds. Once again, keep in mind that what we are trying to do by increasing the number of poles, we are trying to make the profile smoother, but you're taxing your control. You're moving the requirement of what you're trying to do from the designer to the controller. So on the flip side, if you want to go fast, you typically will need to get to a place where your design takes into consideration what sampling frequency you can do. You have to make sure you include what switch you are going to use, what the power level is that's going to have, and whether you can go analog. You might have some restrictions on whether or not you can use a certain DSP or microcontroller. You might end up wanting to go to analog systems if your throughput is going to be faster or your latency is going to be low. So the lower number of poles, like I said, is a good choice for high speed, high efficiency, which basically means you're talking about low, that'll give you low iron losses. The second thing is the air gap. If you are selecting the air gap, you are trying to calculate it for how much torque you want to generate. Your average torque is what you really care about. If you take into consideration your I don't have the so if you take into consideration the actual geometrical details of this motor itself, it will tell you specifically in terms of what the arc angles are going to be. It will tell you specifically how much torque you're going to get. And if you go back here, alpha R is the width of the rotor pole, alpha S is the width of the stator pole. So that's basically you're trying to calculate what the width is going to be, because that dictates how much gap you end up creating. The further off your rotor pole is from the stator pole, that's the amount of air gap you're going to get in your machine. So the question now comes down to how thick can they be? That's a question that I have had come up quite a bit. So we actually have a paper that we wrote on that as well, specifically looking at the profile of the machine for different arc lengths. Can anybody tell me what arc length is or does? I mean, it basically says, I'm trying to see how much this is. Yeah. So it gives you some information here, part of the question that I'm trying to ask. What do you think arc length is or does? Like, what is the role of arc length in the design or even in the torque production capability of a motor? It does. You're correct. How? You're absolutely correct. It does affect saliency ratio. Which variable of saliency does it affect? So when you talk about saliency ratio, it is aligned and unaligned position, right? Which of those two is it primarily going to affect? Actually unaligned. Unaligned. Why? Because aligned position, you have a flux path. If you write the equivalent circuit equation for your inductance, you will write it through the middle of the pole. No matter how wide it is, that pole, the center is still going to be the same, right? Now, you can have a flux path that is defined. You can have multiple flux paths. If you look at the book by Professor Krishnan on switch reluctance motors, you will see he's used 3 flux lines. So we've also done the same analysis with 3 flux lines. We also have an MEC method we have come up with that specifically takes into consideration that. But the point I'm trying to make is that your aligned position goes to the middle. So if it's wider, the impact is going to be less prominent. If you're unaligned, in unaligned position, the distance between your stator tooth and the rotor tooth will change, because if it is wider, they start getting closer, right? I mean, it's like sitting on an airplane. I mean, the bigger the people are, the closer you're going to be. And that's not, once again, that's not hopefully that's not an offensive analogy, but bear with me on that one. But the idea is, if the wider this is, the less space you're going to have. If you have less space, your air gap is lower, which means your inductance in unaligned position starts to creep up. That can be a challenge. So you don't want to get up into a scenario where you indefinitely or without consideration for the saliency ratio. So that was a fantastic answer. That's what you're trying to balance out. You're trying to balance out. But on the flip side, it also does have an effect on the aligned inductance to the extent of how flat and how long that region is going to be. Because once you overlap the stator and the rotor, you can keep moving. The overlapping area does not change. So you have fringing that might cause some differences, but generally speaking, that overlapping area between the 2 poles is going to be similar, which means your flat region on top might extend a little longer, which it might be a wider region. Now, when you're doing something like that, one additional thing to consider is that you need to make sure you de-energize. Like I used the example for the traffic stop, you need to de-energize your phase a little before it hits aligned position. If your phase is still aligned when you go to, if your phase is still energized as you get close to aligned position, that rotor will either want to go away and shoot past the stator, very quickly, or it will essentially go and have a vibration. It'll have a kind of a little bit of a basically back and forth, the swaying motion right at the rotor. It will twang to a stop, so to speak. At the same time, you are trying to make sure that you also having the air gap when you have the right arc length, you're trying to use that also to control the amount of torque ripple. Also, like what you can do for induction machines, you can do skewing. If you have an arc length for the stator or rotor that is too wide, then skewing also can become a problem, because you'll end up going in from one side of the stator to another stator. So you end up skewing in a way that the math might lead to negative torque as much as it does positive. So the longer motor tends to increase saliency, because keep in mind the length allows you that much surface area. So every one of the phases is contributing to the inductance. So you can actually get more saliency out of this. But when you're talking about the longer poles, you need to make sure that these long poles can get a tangential force, and that can also lead to an increase in your iron losses. You need to take that into consideration. So this is the example I was talking about, the reference. So you can see it was published a few years back, but this was actually done specifically for in context of the e-rickshaw. So let me do this. Before we go into this one, I know I'm taking this about 5 minutes early. Let's take a 5-minute early break. We come back. We will start from here instead of starting here and then stop in 10 minutes. So let's say a quick 5 to 10 minute break, or we come back exactly at 11:05. And we'll kind of take off from there. So this should be working now. Yeah. Okay. Okay, so let me just go ahead and catch up here. Okay, so we've been talking about the idea of electromagnetic design of switch electronics machines, right? So can you just activate that? No, activate this one. You had to click here. Yeah, there you go. Okay, now let's go. So, so one thing you will notice is that when we're talking about switch electronics machines, it has potential benefits in terms of supply chain robustness. The idea is that you don't require any for permanent magnets. This in particular was actually done by one of the alumni from IIT in Chicago, who also wanted to have e-rickshaws. We looked at this application specifically because the goal was to have a solution that was the worst application where you could have the most impact. So the original idea that they wanted was a rickshaw with all solar power only. What we found out was that when you put only solar power, it does not give you the amount of required energy for the application, because solar itself is intermittent, which means you're not going to get energy as quickly unless you store it. So the first thing we did was that even if you want to charge a battery, you could arguably do that by storing energy in a battery, but it all depends on how much time you have between two runs. So let's say you're talking about a place like Calcutta, where you have these point-to-point rickshaws, right? They only go from one point to the other and they have stops along the way. In a case like that, sure, then you have some predictability. Evening time, you're going to have 45 minutes. In the morning, you're going to have, I don't know, 2 hours in between days we take the rickshaw. So there might be certain times when all of that makes sense. And for that, if you start looking at scheduling your charging time, that creates an opportunity for specifically identifying where and how that energy is going to be stored. You could have a system in which energy is stored in the vehicle. You can also have an energy that's stored as the buffer in the battery that allows you to have a high speed charging. You might be able to do level 2 or level 3 charging if you have energy buffer stored into your charging station. So looking at such electric machines primarily because it had benefits from supply chain vantage point. We talked about that. We also looked at the fact that this kind of motor has the same field distribution, but it's basically going to give you a much better torque response. The inductance profile I showed you before, that's essentially what you had for the 6-4 switch electric machine. So the idea was, let's start with what we know. Start with the 6-4 machine, and this was right at the time when we developed the idea for a high rotor pole switch electronics machine. This is the equation that led to the start of a high rotor switch electronics machine, HRSRM. HRSRM basically has an equation of NR is equal to twice NS minus 2. What that basically means is that if you have a certain number of stator teeth, stator poles that you know, you can design a system which has an R number of poles in a way that you will not have a locked position. We talked about how you select the number of rotor teeth. This equation gave you designs where you can go from a 6-4 machine to a 6-10 machine. So one of the key advantages, like I said before even, is that when you increase the number of teeth on the rotor, the first thing is you end up lowering your torque ripple. What we normally would have seen for an AC machine, you would have increased the number of phases. That gives you better torque performance. Increase the number of poles, gives you better torque performance. The same way, increase the number of teeth and it gives you much better average torque performance. There's actually one more journal that I did not mention here, from which we got this work here. It is actually by one of my colleagues who was the original inventor for this motor technology, called Piyush Desai, and he worked on this specific topic. I was his co-advisor for the last year of his PhD, and we've published a few papers together on this topic. He still continues to work in the area of motor design for his company, as do the other papers that I've shown you where we're talking about machine design. He is the CTO for another switch electric motor company in Canada. So both of them are very active and engaged in this area, and they have their own outputs that you might be able to reference and learn from. So as you can see here, what are the differences you see? So first thing you notice here is you have a certain number of teeth, and then you increase the number of teeth from 4 to 10. What are the first few things you notice about this design? What are the changes you notice? You have more strokes basically. Yes, you can have more strokes, correct? What else? Okay, it could be less ripple, but geometrically, what do you notice? Exactly, the size of your teeth went down, right? The teeth got narrower. What does that do? What could that do? Narrower teeth means the same amount of current will give you higher flux density, right? You get saturation, which means now you have to start planning for how you are going to design this motor such that you operate in its optimal region. So you might get more torque or smoother torque. The question is, are you going to get better power rating? That's another component you need to take into account. So this is for when we convert it from 8.6 to 8.14. So this one is 6.4 to 6.10. You can go from 8.6 to 8.14. And as you get larger, you will notice this is the one I'm talking about. Let's say you energize phase A. Now you could actually attract 1 or 14. That's a problem. So this is not necessarily a bad thing, because in this scenario you might energize DD prime. That allows number 6 to line up, and then you can keep moving. But the question once again is, in this scenario, what is your saliency ratio? How much unaligned inductance do you have? Because it will control, you get smoother torque, but whether or not the torque is going to be at the average level you want it to be is another question. So when you do the design, one of the components to take into account is actual physical geometry constraints, right? You need to make sure you identify which machine can or cannot be designed. What are the physical limitations for manufacturing? And that defines the angle beta R and the rotor angle, stator angle, called beta S. So in this case, if you had beta R as 21, which was the original number, and you try to keep the same saturation level, now physically it's impossible. I mean, one might argue that what if I actually clip it off here? And I was trying not to, sorry about that. So let's say if you wanted to cut it out here and leave this entire thing, of course, very obviously, you lose out on slot area. So you need the slot area because you have to put windings in there. So the solution is, now you have to make those teeth narrower. So when you do that, as you go from the conventional to, well, at this point it's not as novel anymore, then you actually end up getting to a scenario in which you reach saturation a lot faster. So that means that you have to have a geometric constraint that you introduce into your design process as a function of beta R and beta S. The stator and rotor pole arc have a limited number, and this will automatically affect the dimensional selection that you're making for your machine. So each one of these inductances can be related to the rotor position in terms of which component of your rotor of your design is going to be your constraint. So the idea basically is, if you interchange the pole arc angles, in that case, you can get configurations that are similar. However, keep in mind that the bigger your circumference, the more space you have along the the more space you have, right? Basically meaning, if you are putting the same number of teeth on the stator, which is on the outside, versus the rotor, you might have more space. So if you have an exterior rotor design, but the rotor is on the outside, the stator is on the inside, because of the diameter, now you have a little more space. So you have some benefits of being in the higher, or basically the exterior rotor type configuration. If you're on the inside, you will need to have narrower poles that can then give you the same, the expected performance, but you might have limitations in terms of your flux density. So in terms of the configuration for the unaligned position, there are several equations, and these equations, we have listed them, most of them in the paper, and we actually designed a tool specifically for this. Trying to go back to where I'm catch up. Yeah, so in this case, when you're talking about this one, so if you look at this equation here, you have multiple equations here, right? You have 6 equations that are presented. So if you're trying to find a solution where your objective is to maintain the unaligned position, this essentially gives you the geometric parameters that you need for maintaining an unaligned position. If you don't have a clear unaligned position, like I said, you will end up getting to a scenario in which your torque will not be adequate. So this is actually an iterative algorithm, and if you have a specific machine configuration, that will, if you have a specific machine configuration, in that case, the terms of the length of the stator pole arc, and then you have the length of the arc itself, the unaligned arc, So the length of the arc itself or unaligned position, that will dictate whether the machine dimensions can be achieved, and if so, what optimization. This is the equation that specifically tells you how you can maintain a fully unaligned position, and you define this L un. If your number is not less than L unaligned, you will not get a clear unaligned position for the motor. So the problem that you see here basically is mathematically this like why the idea of converting it from a 6-4 machine to 14 poles did not directly work. So what you see here essentially is that the pole angle, it covers an angle that is 2 alpha plus beta r. That's what the pole itself covers. So when you multiply the number of rotor poles, this value, when you multiply this the number of rotor poles, you end up with a value that is higher than 2 pi. That is the entire circumference. When you do that, obviously you have violated physical constraints. So if you are designing an iterative algorithm, so if you want to design drop-in replacement that has very specific design constraints, and we have actually done a few projects. We've developed a design tool using MATLAB and also using Python, where you can actually design drop-in replacement switch reluctance motors for any given application. And the goal really was to take into consideration all the constraints placed by the application and then come up with a topology that will give you a performance in the dynamic environment. And the reason we are integrating that platform into the multi-physics design framework I showed you is because that now gives us an analytical approach to design the overall drive system. Because constraints are very clear. We know exactly what we need to do. So when I'm trying to modify the motor type and replace it with the switch reluctance machine, the first thing I need to tell them is it possible? Because think about it this way: when you do a project, if you're working for a company or if you're getting a project, usually you have to make an initial educated guess about whether or not what you're proposing could even work, right? I mean, it's one thing to say, well, I'm confident I know how to make it happen. But then you might have scenarios in which your geometric constraints are just not right for the job. So those things have to be done. So these are basically pre-designed calculations that you do. So you can do they often also referred to as pre-designed qualifications, specifically to see if a specific given motor is suitable and fit for the job at hand. That's one of the reasons why you use options like MotorCAD and such. ANSYS has these tools, front-end tools where you can do, but that's once again an iterative algorithm. How can you know or how can you know that I can change the current and that will give me the required amount of torque? So if I go into single pulse mode, I will get the efficiency numbers I want. Or if I have the stator diameter be small and the rotor diameter be large, maybe then I get the torque I want. But you have to have some mechanism, some system that actually analyzes every possible combination of the geometry specifically to tell you whether or not any of them gives you a drop-in replacement. Otherwise, you might have a small variation that's possible. In particular, just think about the idea of the slot. We talked about permanent magnets and the slot that comes with it, the notch that you have in the rotor structure. That gives you a substantial improvement in your torque ripple. There's a reason why they were doing that, but you need to know where to place the slot with designer experience, or you have to have an automated process that does a sweep and specifically identifies what that optimal slot geometry should be and where it should be placed, right? So, so here basically you have your rotor and stator poles need to be wide enough to carry the required amount of flux, because otherwise it ends up getting saturated. So now this becomes the configuration in which you have two configurations here. One is in which your length of your phase is basically the diameter of your stator core, rotor core is 11-inch, and your phase is basically is 11. And what you see here essentially is the first SRM that you have here, your beta R is higher than beta S, which basically means your arc length that you have for the rotor is larger than the arc length of your stator. When you go to the maximum electrical angle, your rotor pole arc is closer to the line position. What you see here is when you go from beta R larger than beta S to beta S larger than beta R, the average value of torque is not very dramatically different. In terms of the flux density, they are different. So if you look at this one here, this is 1 Now it's 1.12, this is 1.4, becomes 1.56. So there is a difference in the field distribution that you are getting inside your machine for both these configurations. So, and that essentially means that your magnetic flux density at your rotor pole can be smaller in specific scenario than it is for the stator, which means that your beta S larger than beta R gives you more flexibility if you want to have a complex design. So if you want to have a complex design, then the condition of beta S being larger than beta R can give you more flexibility in getting machine design and a compact size. Okay, so also because you have the higher number of poles, a smaller pole R basically will give you the same area for given number of stator arcs. So self-starting basically is the condition in which you are able to, like I said, start the motor at any point. Okay, so self-starting means if you apply current at any given rotor position, there's always one phase that you can energize to move it in the direction you want to move it. Well, so you have to have the ability to go from unaligned to aligned position, and you have to have motion, or you have to have the ability to go in the direction of motion you seek. So the minimum arc angles can also be calculated for the starting. For self-starting, you essentially are first and foremost, you're trying to make sure that you are designing it for every specific angle. If you don't calculate the specific rotor position at which you are analyzing, you might still have one position where it is going to go ahead and get locked. I know there's a lot of mathematical geometrical calculations here, but it's not electromagnetic in nature. These are geometric designs, geometric constraints we're talking about here. Once you combine them to field distribution, that becomes a tool that you can actually use. So you need to get to a place where you can select the value of beta R, beta S, and beta R, and your rotor arc length must be higher than this value to have non-overlapping inductance profile. So if you go to a condition, specifically if you analyze the behavior, you can see what happens when each one of these angles. There's a small difference you will notice between beta S larger than beta R and smaller than beta R, and the inductance values at the minimum minimum condition is also given here. So if you take it one step further in terms of configuration, you can decide which angle makes most sense for a given geometrical constraints. I know I was dwelling quite a bit on this topic, so I'm trying to speed up here just so I can kind of catch back up with the design considerations. So for this specific equation, what we need is that we need to make sure that for non-overlapping inductance profile, our generalized equation essentially is that the sum of the arc length of the rotor plus stator needs to be larger than this predefined threshold called theta RS, which is a geometrical function depending on number of rotor teeth, number of phases, number of strokes, and number of stator teeth. So basically, you're taking into consideration all the geometrical features and allowing that to calculate what that total arc occupied by the rotor plus stator is. Basically, what you're saying is, if I have two arcs and I put them adjacent to each other, they should give us enough space clearance that I can still get an unaligned position. That's the bottom line. So for our condition, specifically for self-starting, we identified what that design criteria should be, and we identified also that if you want to design a motor where BR, Y, and HR that you have are the parameters. These are basically is the volume, the use of the active material components that you are going to use here. So what this basically means that you have to maintain what the maximum value. If you increase HR, in that case, HR is this rotor pole length here you're talking about. If you increase the height of the rotor pole, in that case, the maximum value of beta R you can get is going to be smaller, which means your construction of the pole is essentially could possibly lead to a narrower rotor pole. So think about it this way. You have, if your diameter is larger, like I said, the higher up you go in the diameter, the more space you're going to get. Of course, as you get the longer, your structural integrity becomes a question as well, because if you're getting longer, in that case, you might end up getting more deformation where you end up getting some lateral movement. So if you change the stack length, now this is another design constraint. If we're talking about changing the stack length, stack length directly has an impact on torque production, right? So if you're talking about, if you keep the dimensions of the entire motor constant and you increase the stack length of the motor, in that case, the inductance, torque, and the back EMF of the motor will change. The magnetic saturation profile for the motor will remain the same because the field distribution is happening in the XY plane. So if you change the stack length, what did not change is how much flux is flowing through it, right? The plane of connection is different. So if you increase the stack length, your torque goes up, and that allows you to get more torque production, but every other variable stays the same. So if you want to reduce this magnetic flux density, in that case, your outer diameter of the motor would need to be changed. So we have defined, basically going back to what we talked about, all of these equations are from the original electromagnetic analysis we had done, right? We were talking about the definition of reluctance, flux density, we have inductance, and then of course you have the force on the wire itself. So these are equations we are very familiar with. Based on that, you can define specific geometrical constraints that will allow you to decide what your back EMF on your machine is going to be. Why is this important? This goes now to the inverter. You have to know what the battery capacity of your system is, what the DC link voltage is going to be, and correspondingly, how many turns can you give? Because this E, while it tells you K times omega M times I, it also will be broken down in terms of I is broken down in terms of N times I. How many amps versus how many turns, right? You're talking about H. H basically is N times I. One question that actually came up as we have published in the journal, one of the questions that came up was they were saying that when you increase the number of teeth on the rotor, you might end up with a negative torque because there is still a tooth that is in close proximity to the stator. So in order to verify what that does, we actually eliminated in the design, we took out one of the teeth, one of the tooths, so on both sides. And we applied current to see what the difference in our torque reduction was. The reviewer was correct. There was a reduction in the peak value of torque from what we had without the adjacent pole. The peak value went up. So the average value went up by a little bit, but the peak value went up by a substantial amount. And that was, it's not a limiting factor, but it's certainly a geometrical or consideration that you have to take into account. So the larger machines would give you a little more space, and therefore you might not have to worry about the absence of negative torque or the presence of negative torque. So what we said basically is that in this case, we identified from this that having beta S more than beta R is a very good way to design a compact SRM. If you have a small difference between beta S and beta R, in that case, you don't have to have a major impact or major influence on the inductance profile. You don't always need to worry very uniquely or very specifically for each machine design. When you're talking about the motor itself, you need to have constraints on the control. That control is most effective when you combine the design along with the control. So if you are doing them both simultaneously and you do a co-design, we found that out to be most effective. I will talk later about the co-design framework that we have done for this kind of motor, where we did a behavioral model and I can embedded that into Simulink. So by changing the number of strokes, we were able to get much better performance, but we had to define this constraint because beta S larger than beta R was not a constraint that was previously recognized. So if you take it one step further and look at what the profile for each one of these currents look, this is the output for torque and speed. So you have the torque, you have the magnetic flux density, you have speed, torque, inductance, flux density in the stator, and flux density in the rotor. Why is this important? We need to know what peak flux I'm getting in my lamination. If my lamination material cannot handle that flux density, then I will get to a scenario where I will create hotspots, or worse, I'll end up with losses because I'm assuming that my flux will go linear. In fact, one of the simulation software, I will not name them, would actually assume that if you applied a lot of current, it would let your flux density go up to 2-3 Tesla, and it would not stop you. That's a fundamental challenge. You should not have a system in which it shows you the ability to take your flux above what the material properties should identify. It should tell you or have warnings that should be created along with it. So the way we start the SRM design oftentimes tends to be you do static simulations. These are all static simulation models in which you can apply the current for each position and take it across the electrical degree, going from unaligned to aligned position, unaligned to unaligned, and you basically will get essentially a mirror image on this side. You apply current in the positive inductance profile and the negative inductance. Basically, you're applying current here and you're applying current here. If you wanted to look at how the SRM operates, take each one of these phases, start stacking them together. If you add them together, you will get the resultant torque you're going to get. Now, it's a little more complicated than that. It's not quite as simplistic, but effectively that's what you're doing. You get torque from one rotor, you put the next one, create enough of an overlap so when they start to drop, one's dropping, the other one's picking up, the sum still stays where your tangential force, it adds, right? Normal forces don't add, but the tangential forces do add. So the ability to add the tangential forces means as long as you have a good amount of overlap, you can get a very good performance. This was the motor we designed in our lab, and we basically went for, this is the FEA model, the lamination for the motor design. This was the final motor that we designed. It had 610 configuration. This is the prototype assembly, just to kind of give you an idea of what this was. This was actually a motor in which we used an existing housing from before. The challenge we faced was that because we did not plan out the motor entirely, we ended up with a housing that fit, but we actually had gap in the front and back a little bit, which means for this specific motor, our acoustic noise measurements would not be practical because you now have created an acoustic chamber within the housing that will not exist in the real application. So that was a little bit of a learning moment for us when we went about the housing design. This is essentially the test setup that we had. We put on the outside, we actually put a lamination just to be able to see what this motor would look like. And I can show you some videos of it operating as well. It was meant to be for the rickshaw, so we actually had a battery pack that goes with it. We designed a battery charger that goes along with it as well. Connected the motor, it's a 5 kilowatt dyno tied to it, inline torque meter, Lovejoy couplings, the controller for the motor, and a position encoder. And this is the motor that controlled the SR, and that's the PC that controlled the dynamometer. The test setup was fairly standard. Everybody has something like this in your labs. It's not something very unique. But what we did specifically that was beneficial for us was being able to embed, and this is some time back, so we actually embedded the simulation model of FEA into Simulink. And that gave us substantial benefits in identifying how this system operates. What we have here in our case, we actually used 4 full bridges. We were trying to identify the best control. Said the original design we did was a sequential design, which means we designed the motor and then we designed the controller. That's the model, that's the thinking that we changed a little after that. So until then, we tried to make a converter that would give us the most flexibility, and that was the full bridge. What that did for us, of course, as a problem was we now designed 2 converters. The first one to give us the most flexibility, but it was not representative of the actual application. And the second one, which we actually were designing. So you can see how it actually adds an extra step to this entire process. The same thing as well, if you're designing a converter that, let's say you have an asymmetric bridge available from before. Great, it gets the job done unless your current sensor is, let's say, designed for 25 amps and you are never going to go above 5 amps. The resolution of a current sensor is going to be filled with noise, right? When you measure it, your resolution of your sensor feedback is going to be very limited. So the reason I keep emphasizing on the fact that we need to have a hardware representation on your system specifically means that you need to see what it looks like with a hardware in the loop system, either a hardware in the loop system, or you need to have an actual emulator that is integrated into this machine. So just to kind of, we had another comparison we did specifically to see what happens when we, if we have a 6 versus 610. We have the same geometry. What if we don't put 10 teeth? We still have more poles. What if we have 8? Because that was a question. The pole design formula we had, the PD formula we had, gave you NR is equal to twice NS minus 2, NS plus 2. What if it was not NS plus 2? What if it was NS minus 2? What if instead of going from 6 so basically to 10, what if we went to 6 to and 8? So that was a question. Do we still get the benefits? That was the question we were trying to answer. So a few key differences when you make a geometrical change, and this was important in our own understanding, was the width or the how wide your inductance profile is starts to change. When you went to when you were at a 6/8 machine, as you can see here, the unaligned inductance is lower. Why is that? Because you have more space on your circumference. Your unaligned position is your rotor tooth is further off from the stator tooth as long as you have the same width. If you increase the width, now that changes the game altogether. But for an apple-to-apple comparison, if you do that, 6/8 would be a much narrower inductance profile. The other thing also is you will notice is that it has a much steeper inductance curve, which means I squared dl d theta would mean you get a much better torque performance, or you would basically get a higher torque out of it. So interpolar gap is higher, which means your flux is going to travel a longer distance. You will have a lower unaligned inductance, which intuitively seems like it would be a bad thing. It's actually not necessarily. If you look at the torque that you're producing, what's interesting to see is that your peak value of torque does go up, like what we were expecting. However, what also changed was the duration, the width of my torque profile for the 610 was wider. What that meant was the area under the curve did not give us necessarily the problem that initially we might have thought it would have, right? Because if you went higher, the assumption is you have higher torque. Therefore, you're going to get better average torque. Not always, unless you can make it wider, in which case your ripple goes down, but you can still maintain at least the same torque, or in some scenarios, you can actually get a higher torque from that as well. This is the comparison for the torque that you get from both of them. The peak here is somewhere around 25 Newton meters of torque. For this one, it's about close to about 28. The minimum value here is about 5 or 6. The minimum value here is higher than about 12. This automatically tells you your average value might not be that far off, but your ripple is substantially lower when it comes to a 610 machine as compared to the 6/8 machine. And that was really an important finding for us, because the question, of course, comes down to what if instead of 6/8 or 610, what if we did, I don't know, something like 620? There is a design trade-off. It's just like the number of phases. If you increase the number of phases from 3 to 5, you have a benefit. 5 to 7, sure. 9, you are pushing it, right? Because at some point, the geometry of the machine does not give you the benefit. It's the same as transmission line, right? There's a reason, if you have done your fundamentals of power back in the day, we start talking about why we supply power using 3 lines, why it is not single phase, right? And why do we not have a 5-phase as opposed to, or 7-phase, 9-phase? Because the value that you get by bundling 3 conductors, 3 phases, it diminishes. It's a law of diminishing returns. You don't get the same improvement for the cost that you are going to pay for it. So what we also found here was that 610 finishes 1 stroke in 36 degrees, 6/8 finishes 1 stroke in 25 degrees, which basically means in a 610 machine, the magnetic field is 1.25 times that of your 6/8 machine. So it could be looked at one of 2 ways. One is you have to have better steel, or 2, you have to have better control in your current, and you should not send the same amount of current that you were sending through a 6/8 machine. So the discussion point basically here is that you get much more flexibility in the 6/8 machine design. 6/8 has lower cost, but 610 has a much smoother torque profile because of the higher number of strokes we are getting. The average value of torque was also higher. So the metrics of interest that we like to see in the SR, several of them had substantial benefits. It was the challenge, of course, is that my 610 machine was spinning at 1.25 times the fundamental frequency. What that means is that my sampling, my processing, all has to happen faster. I did shift not the stress, but I did shift the complexity from the machine to the converter, with the understanding that my converter can handle a lot more than a motor. My motor has real physical constraints. I only have so much volume. Torque ripple is a function that it's a motor output. I cannot change torque ripple by just controlling power electronics. But in power electronics, I can get a faster switch. I can get a faster device. I can have a much better bandwidth with better resolution in my sensor. So the understanding was power electronics is advancing at a much faster rate than the machine physics, electromagnetics allows me to. So that's why the shifting of the complexity was, in our view, a very important step in the right direction. So I'll actually show you at the very end. So as we're doing this, let me do this very quickly. I'll talk about all this later, but I'm trying to, I should have put this here. When I was placing it, I looked at, I should have included this one here at the very end. There is, and I'm going to make sure that we cover most of this stuff. There you go. So just to kind of give it, I should have put this in there. So just to kind of give you an idea of where this technology went. So we started off at IIT. This was 2007 and 8 when we got the first patent. Since then, it went to a company called HEVT, Hybrid Electric Vehicle Technologies. They had exclusive license of this product, of this specific patent. They got bought out by a company called Software Motor Corporation, which became Software Motor Company. And they actually took it to a smart motor system. They got major investment. They went to, they rebranded themselves called Turntide Technologies, and Turntide Technologies is silicon. This is when this was from IIT to an incubator, from incubator to Silicon Valley, and Silicon Valley to major investors. So it's now actually is called Turntide Technologies. They're based out of Sunnyvale in California. They have a bunch of offices. They also bought out a couple of companies in UK. They actually bought out several. So when we started, it was just in a lab with just a couple of students. At HEVT, there were about 2 or 3 of us. And then at Software Motor Company, there was 5 of us who started, and I was one of the original ones. I was not an employee of the company, but it was something that started. And at Turntide right now, they have somewhere around 600 odd people. And this actually was a month and a half or 2 months back. They just exceeded a 1 billion valuation for their company. Now, once again, that 1 billion only means something once you go public. If you go public, that means you're a billion dollar company. So it's a big step to make if you are able to IPO, if you go for a public offering. But the point I'm trying to make here is that the idea that started was not necessarily with the intention that we're going to have a new company. We were publishing like anybody else. And we had some other questions specifically about patents and what you do. There were lots of lessons along the way that we have done. When you should publish, when you should not publish. What you should first patent, put a provisional, and some things you should not do. So I'm more than happy to talk about some of our lessons. We've learned, like I said, lessons learned the hard way, several of them, to where now, right now, I have a few patents with this company. I did quite a bit of work with them after that. And so this was a time when we had about 5 or 6 people. We were working on sensorless techniques and everything. And now they are turnkey solutions. They work in electric vehicles and also for rooftop units, RTUs and all that kind of stuff. So I can share some more details. You can go and check out the website, turntide.com. They still are there. And the invention, like I said, was Pierce's. I just want to make sure I'm not taking credit for something that was part of his PhD. We were a team that worked together. We had lots of patents, lots of technology, but the point being, the market was very hot. Investors for this actually includes Amazon Rainforest Fund. Amazon Rainforest Fund was one investor. Bill Gates has his Footprint Capital, the one that has Bill Gates and Robert Downey Jr. That's Iron Man. So they have, Robert Downey Jr. doesn't have the same effect as Iron Man. So they are investors. BMW iVentures has invested. Ansys, this CTO of Ansys is on the board. SoftBank. So there's a bunch of investors, the very large investors who are actually involved in the company. But that's not to say, this is not to kind of talk about where we have gone as much as saying when we started off, we had no idea what we were doing. I'm not entirely certain right now the technology is completely commercializable. The market right now in the last 2 years changed dramatically, right? The market is going up very sharp. And then over the course of time, all of a sudden now, all the public offerings have kind of are teetering a little bit. Going public has questions about what can and cannot work, what will or will not work. Bitcoin went from what it was to what it is, right? Tesla reported this morning, I just saw this morning in Wall Street Journal article that said that their winning streak of record profit has just stopped, has ended because the plant in China closed down. The point I'm trying to make is that technology is very important. It's important to have people who recognize the value of technology and be ready, because you don't know when you're going to go through that journey. You cannot start assuming you're going to go and build something that somebody's going to buy. But anyway, so all right, so now I just realized I had to skim all the way back. And I'm realizing that I'm going to be short in time. It's definitely guarantee. I'll go over the geometrical part much faster this time. As I said, I've worked on SRM long enough to where I have a lot that I can share, but I had to cut my excitement. So basically, when modeling, you can do multiple things for modeling, right? The first thing is really our idea was we have done FEA, it took too much time. And so the goal was really to convert them to a model that allowed us to integrate that into our simulating block. So we used the principles, we created a lookup table based method, and we used Steinmetz equation specifically to calculate core losses. The idea was combine ANSYS, which now we've actually moved from Infolytica to ANSYS. We've been using that for quite some time. And we combine that to create an inductance and static torque profile. From that, you create, basically, we're doing a way of mathematical reconstruction that allows us to calculate the torque. I told you, each one of the phases, you add them together, you can create, if you know the flux density and your static torque profile, you can combine that to recreate the behavior of the motor. So I put this in specifically so that anybody who's trying to design this in ANSYS, I know towards the end, we won't have time to go over a modeling detail because license for ANSYS is not available. But I asked one of my students to kind of put together the steps just so that when we are talking about this, if you want to go back and reference how we did this, we have a reference available, which, by the way, the folks at ANSYS are always happy to work with you. So if at any point you have a question with them as a university student, you have substantial benefit that you will never have as when you're working for a company. The software is obscenely expensive at a company, if you think about it, but at a university, they provide sponsorship, which I'm sure a lot of universities already have. So you can basically do material assignment. From there, you can select what property you want to have. You just define what the permeability is going to be. You can modify the BH curve if you want. From that, you set up your simulation. Once simulation is set up, you can set up what your the solver setup is going to be. And I have, like I said, I have comments that I can give you for each one of them that I can share with you. These are not steps that are super novel, but I wanted to have them because if we don't do a hands-on exercise, having this might be of relevance to you. And then, of course, you go into design properties. You need to make sure you go into design properties, select what your local variables are going to be, identify a time step. If you haven't done, some of these can seem a little daunting, but it's not nearly as bad. Once you do it a couple of times, it actually is fairly repetitive in its behavior. After that, you go into reporting, set up your rectangular plots, make sure that your output is going to be what you need it to be. Define what output variables you're going to see, whether your phase inductances, flux linkages, voltages. Take it one step further, define the reports, calculate the fields, set up the control circuit. The control circuit, we actually started integrating them into our topology here. Select it's an external circuit. Define the external circuit. I think we put in a whole lot more detail than I had initially intended to. And then you can actually set that out to an external circuit here, and that will give you the entire profile. The goal was, using all of that, create a model that gives me my flux distribution. Why? What we were trying to do was we were trying to calculate the core loss inside the motor. We were trying to figure out how much loss we are going to get in order to calculate the efficiency in our simulation model. Because when you do a simple Simulink model, it's easy to calculate copper losses. It's I, you know what R is. You can do a 4-probe test. You can basically do an LCR meter or something and measure the resistance of the winding. I squared R gives you the copper loss. However, what you don't get is iron loss. What about the iron loss? You still have to account for that. It's not as negligible as you'd want it to be, especially if you want to extrapolate that information to get it to thermal behavior. So we basically probed the system for flux density on both the teeth. From there, we also did that for the yoke. And then from the core lamination, we defined each one of these segments as one place, one of the portions of the motor where we were probing. And the idea basically was that we figured out we could do this in many ways. Either we could have a core simulation model, lookup table, or what we did here, which was the analytical model. So we input that information into our inductance torque flux density model. We added the losses here, and that gave us the overall efficiency that included the loss behavior from magnetics and from my power electronic domain. So the copper losses and core losses were adequately represented. We did check to make sure our numbers were right. We compared the numbers with FEA, the core simulation model we had from FEA, and we compared that with the results we got from our simulation model to make sure the numbers matched, and they matched perfectly. This is basically the setup, the phase currents for comparing it with experimental. So the first one, the top one is experimental, and the bottom one is simulation. For the same operating point, the result is very good. Of course, you see a much larger ripple because this was not optimized. It was just, we just picked a point and we wanted to see if we could recreate that point on FEA. So the core loss, in terms of comparison, what we did find out was that the core loss had a very good correlation with what we got from the estimated value. So if you compare the actual value to estimated value, we were within barely about 1.5 to 2%, sorry, 1.5 to 2 watts of the numbers. And this is the maximum loss was 1.4 watts, and we were within a 5% tolerance. What that told us is that using methods like Steinmetz equation, which is a well-established method, it's not, the equations are not new, and you might have seen them before. So it's a standard equation, but using them into your behavioral model allows you to extend the capabilities. The reason why I thought this was particularly useful is because this cut down our simulation time from a few hours to a few minutes. And that was a huge difference for us, especially as we were changing. We started modifying the geometry because that was the next step I told you we were starting to do. We were trying to change the geometry of the model repeatedly. So we would parameterize the model on ANSYS, and we would start getting samples of flux distribution. And then we could start to train our system to identify what controller gives me what efficiency for what operating point. So very quickly, the discussion point would be, if you're changing the fundamental frequency, what happens to the what happens when the number of poles are increased? And of course, how does it affect your hardware setup? I think I already answered these questions as we were talking. And I just wanted to quickly get an idea from you on what you think. I mean, we talked about this, so arguably you should know the answer. What do you get? So if you have, if what changes are you expecting? If you change the number of, if you change the fundamental frequency, or if you change the number of teeth, what happens to fundamental frequency? If you increase it, it goes up, right? So the frequency goes up, which is not helpful to us, right? So hardware setup, what does it do based on the experience of hardware setup? What do you think? What do you think it could do? I mean, obviously, because you have more work on the controller's part, right? You're going to be faster. You might need a DSP that's faster. You might not go with, hypothetically, you might not be able to use Raspberry Pi. You might have to go into an Arduino or something, right? Or you might have to use a DSP. So depending on the application, you might have some change in your processor capability. Your clock frequency that you have, you might need to go on from a processor with a single core, like a 28335, to a processor with 2 dual core, like a 28377. By the way, I talk about it all in Texas Instruments terms because that's what I grew up with. So most of my projects were all done using the TI family, the TMS family. So is everybody here familiar with the processor I'm talking about? At least you have come across. Okay, so I know that labs here actually do have DSPs at IIT Gandhinagar. I would imagine you have something like that in your setup as well. But the idea basically is your hardware constraints change there. Next, sensors. Your sensors have to have a response time, right? You need to have the resolution, your throughput has to be good. You might get to a scenario in which you have to have analog set up so that you don't have the ADC, any ADC error. You might have to convert them using an analog setup so you can get much faster response time. You might need to end up creating or changing out from having individual phase sensors, let's say in voltage, to estimating some of these quantities, because you can use switching cycle and let's say the DC link voltage to identify what your voltage level is going to be. But the point I'm trying to make is that your system, if you increase the fundamental frequency, there is a cost to pay, which means there is a cost on the converter side. It can be addressed if you know what it is. So there's nothing called a free lunch, right? Whenever you change any setup, that's how it operates. So as we go forward now, what I'm going to talk about very quickly, I wanted to show you guys this one MATLAB-based machine design tool. I will not go all the way. I'll finish this one. There's a section. Now the sections get smaller. There won't be like a 30-minute slot. But I just wanted to close the loop on what we talked about for the design. This is an FEA MATLAB-based machine design tool. You can actually see I should have put the, oh yeah, references here. Yeah. So there's actually a paper that we talked about specifically about creating this design tool for the SRM. And this actually was the tool we created. So the idea was you start off with the front end, you put in all the design parameters, it gives you set up the simulation parameters using Infolytica. We modified this next round to take it to FEM, because Infolytica was something that you had to pay for, FEM was free. So we've realized we didn't need to have Infolytica. We could, or Magnet, we could go with FEM. In fact, we not only ignored and went past magnet, we also went past MATLAB. We replaced MATLAB with Python. So now the current version that we have for pre-designed tool is it combines Python along with FEM. So it's all of a sudden becomes an entirely free FEM solver that you can use to identify the performance parameters of your machine. So you do FEM simulations, that gives you the static profile, you get the inductance profile and the torque profiles, it plots it out for you, and then it also gives you runs the simulation, and it gives you the dynamic profile in your motor. So it runs everything, extracts the results, and gives it to you. This gives you the option possibly to close the loop from here and give it a parameterized value. So it will actually co-design the motor and the controller, showing you in each scenario what your current profile is going to be. What I found out was that the video that I have here does not work because I was going to do a demo, and I will try to see if I can find the demo and post it if I can. At the very least, I'll post it to my lab website and share the link out for you guys to take a look. These are the polar coordinates. A lot of mathematics that we already talked about. We're talking about winding extensions, talking about this overlapped, the coordinates for the edges on the stator pole and the rotor pole, cross-sectional area for each one of them. The handouts I'm giving you has all of these equations, so you don't have to be too concerned about not having them. But each one of these steps requires to have careful calculations on the values. If you do the mathematical analysis, from there you can identify what your number of strokes are going to be in your simulation, and that takes you from the model to the overall design spec. So you start with the rotor position at the very top, and you work your way all the way down to your analytical model calculation, and that's what the process is that I showed you a little while back. You can do the same thing with ANSYS. This is something that we did recently as well for all of our designs. And this was initially, if we had licenses, this is the demo I would have done, in which you use Maxwell 2D. You basically import the models from here. You can essentially just draw half the motor if you want. Set the stack length, define it for inductance analysis. From there, for a 12-8 machine, I gave you the steps here, like I said, because it is always difficult otherwise to show you in real time. It takes a whole lot more than 1 hour to run this. So you can create, and then you unite the rings and the teeth. You need to make sure they are not individual components. You set the boundary for it. You have a setup that goes for transient motion. Excite it, mesh it, do the analysis, and then you create the results. So the idea basically is that the tool that you use for analyzing a machine does not have to be uniquely different. You have the option, if you understand the basic physics of what you're trying to incorporate, you can break it down into its constituents. The reason yesterday I talked about microscopic energy conversion was very specific. I wanted to make sure you understand that you can break down all of our complex geometries into some unitary features. Some of them might be mathematically more intense, like I said before, we're trying to work on kernel-free methods, looking at electromagnetic fields like fluids that are flowing, right? Like a fluid goes in a continuous boundary. That's more mathematically intense while you are setting it up. But once it's done, the process can be a lot easily automated because the front end is all that takes the effort. The field results can be plotted from here. That then can be brought in. All of your analytical model can be brought in to your profile to create that dynamic model. So when we come back, we will start off here. We take a break at 12:15, right? What time do we normally take a break? 12:15. Next, I have 5 more minutes. Do you mind if I go the 5 more minutes? I'll just go ahead and take it. So here's the analytical modeling of HRSRM. Because if we're done with this early in the third session, we're done with this early, I would like to talk a little bit about what we have found from the practical perspective. So I have plenty to share. I just want to be careful about how much time we have. So this actually is an analytical modeling approach that specifically we used to create the framework. Like I said, we have taken different perspectives at different times. We have tried to do co-simulation. We have done an auto-calibration model by specifically identifying the field, by identifying the inductance profile for a motor from the experimental setup. We have also gone into creating an analytical model that does MEC, magnetic equivalence circuit. This one is basically for incorporating the fact that we are talking about a nonlinear model. It is specific to an HRSRM model because what you will notice is the HRSRM model, the inductance profile is a little flatter. When something is a little flat, that means you have less resolution. So you might need more degrees of calculation. Also, 8x6 SRM had that benefit where you had, if you aligned one position, you would also have an automatic one phase goes to unaligned and the third phase goes to midway. 610 does not have that benefit. It only has 3 phases. So you don't have that benefit. So we have to identify, how do we create that model? So the principles of modeling basically was, you need to have the right inductance flux model, you need to measure the parameters, and of course use them to create the back EMF and torque profile. So as I said, we wanted to have a generalized geometry based model, and the truncated Fourier series basically was built on a similar platform as what has been done for the conventional 8-6 machine. What we have essentially is inductance as a function of position and current, which is defined as a truncated Fourier series, which basically means you have L as a function of I and position and an offset, right? So for 8-6 machine, you had unaligned, midway, aligned. So if you see this one is aligned this way, this one is automatically unaligned, this one is automatically in the midway position. That was a substantial benefit of having an 8-6 machine. 610 does not give you that benefit. So if you look at a 610 machine, your inductance flux linkage, we already know, has different reasons why they can be influenced, and hardware measurement basically needs to be added. So the goal was, what if we could incorporate specific metrics of test from my hardware to make my model of inductance for the motor to be more accurate? Because if you do mathematical calculations but you don't know the design, then what? Can you calculate the inductance profile? Because we did some testing back in the day, we compared FEA with hardware. We are by design simulating a 2D model, right? A 2D model, why? Because it's faster. You could do 3D, it just takes about 2 or 3 times the amount of time. The challenge with 2D is that you don't take into consideration the end turns. The end turns of your motor would have a substantial amount of coil that is turned around. You can put a percentage increase, but now you are guessing. It's an educated guess, but it's still a guess, right? So instead of doing that, what we said was, what if we do specific test, align it, get the measurements, incorporate that into my model? Now I have an auto calibration model for my motor. 610 had some challenges. So this becomes my matrix. So L is a function of basically was a fourth order function in which you have this matrix that is formed. So you have LA, B, C. These are the phases. So it's something similar to what we're doing for vector control, but not quite. We are breaking this into individual that we can measure. So the relationship between the inductance and phase current can be modeled, and you can actually do a curve fitting. So the curve fitting is based in terms of 4 functions. You have AN, BN, CN, and you have UN. When we recreated that to verify whether the model worked, we actually saw that the inductance at 45, this is 25 amps, this is at 5 amps. The numbers are fairly consistent. They do have a 3-dimensional relationship with phase current and rotor position. So if you're modeling the back EMF, the first thing that you need to know is that your E is a function of omega dL d theta. We talked about that at the beginning. If you know what the equation for L is, you can derive what the equation for EB is going to be as well correspondingly. And for that, using co-energy, you can also calculate the torque. Why? Half I squared dL d theta. So we know what that is. You can use the co-energy equation. You can calculate the derivative with respect to position. Based on that, if you're talking about hardware measurements specifically, you can actually look at the applied voltage. This is the current response that you get, and from that you can calculate the inductance of this profile. And comparing them, we actually found when you are at higher currents, which is at lower, at higher currents we had much better correlation. At lower currents we had a little bit of change. The simulation actually assumed it was a lot narrower and as opposed to the hardware. But we tested this model for everything from 5 amps all the way to 80 amps, and the numbers matched very well. The back EMF from between the actual and the simulation model also compared really nicely. And this told us that we don't necessarily have to have FEA into our behavioral profile. Take that one step further. Look at the dynamic simulation. Dynamic simulation also gives you, this is with respect to speed. If you do co-simulation versus the analytical model, the numbers were also beginning to match really well. So this tells us, if you want, like I said, if you look back, I think the paper that we wrote was in 2005, I think, if I'm not wrong, the auto calibration paper, and it's an IAS. So you can take a look at that, tell you specifically what was done for an 86 machine. The version of that we published here for an ITech conference was about 3 or 4 years back. The result of that dynamic model showed us that if you do a code simulation versus the simulation using the lookup table, the LUT, they matched well, but the torque did have some variations. The variation is not big. We went from about an average of about 1.25 to about an average of 1.5. So the observations we had along this was that it was substantially beneficial, but there was scope for us to fine-tune this model. We wanted to make sure that we could characterize the inductance as a truncated Fourier series. Why? Because we understand the math behind it very well. If we can eliminate finite element analysis, the modeling process itself gets quicker. But the biggest thing that we want to incorporate is the hardware measurement into your simulation. If you're doing a behavioral model that is inspired not by FEA, but is inspired by hardware setup, it is beneficial. The challenge or the limitation can be that you do not have the initial geometric behavior or geometric design from the manufacturer, which a lot of manufacturers won't give it to you, especially if you're talking about an end user application type product. So essentially, we found out that it's quite possible. It can be done, and this method can be used a step further for fault diagnostics and isolation. Because if you know what the healthy machine is supposed to look, now you can start to look at the harmonic, you can start to look at the frequency spread and identify if there's a bearing failure or something like that. So that's where we're going to stop here. So we're going to take a pause. I went through that substantially faster than I normally would, not because I don't want to spend much time, but a lot of it is design based. And I want to get to the place where we talk a little bit more about the far end of the control as well. I will also have spent some time talking about sensorless controls. When we come back, this is going to be a little bit of talk about sensorless control, power electronics. So let me know if you have any questions. I'm more than happy to answer any questions you have about anything you see. If there's anything in our papers that you think was useful, there are some references I'm providing as well. You can take a look at them. There's a lot of work happening. The point I'm trying to make is that if you're working in the area of motors, it is quite hot. There are not as many people as you would think, and innovations need to go through the proper commercial cycle. So if you have any questions, talk to me, talk to any of the faculty here, talk to any of the experts in the industry, and I'm hoping that we can go somewhere with it. All right, guys, thank you very much. We are going to come back at 2 p.m. We'll go for the last 1 hour session for today from 2 to 3. In the meanwhile, enjoy your lunch. I'll see you very soon.